Folks, the time is now 8 o'clock. My phone, for whatever reason, did not play the song I expected it to play. So you deserve a song, though, so I'm going to go ahead and play it. Here we go. There. It is 8 o'clock. It is the beginning of class. All you need is love and a math class at 8 a.m. So, okay, there we go. Folks, today we have a quick message from our coworker here, Andy Leonards. He represents the honors department. He is our honored guest today. So I'm going to let him speak to you for a few minutes about the honors program, which is really cool. So take it away, sir.
Thank you, Professor Gabardine. Welcome, everyone. Glad to be here with all of you today. You are in for a great semester, it looks like. This is pretty fun. Your instructor even's got some jokes for you at 8 a.m., right? It's going to be a good time. I have a way we could even enhance this experience a little bit, as well as getting all of you some money. Does anyone here be interested if I said I was handing out money today? A couple people? What we have here is Gateway's Honors Program. Has anyone here ever completed an honors project before?
Where? In high school.
In high school? All right, that's probably going to be pretty similar. There might be a little bit different benefits here today, right? Usually there's somebody who completed one I can pick on, but let me explain how this works. So for honors, there's a couple of qualifications. You need to have completed at least 12 100 level credits. And that's at any Maricopa Community College. So Gateway, any other schools you might have gone to. And then you need to have a cumulative 3.25 GPA. And if you meet those requirements, you're in. You get to participate in honors. Now, by participating in honors, you get a couple of things. So what you're going to do is complete an additional project in this class. The most common one that people are going to do is a research paper. And for that, we have what we call a rule of 10, just to keep it simple to remember, which means the paper would be 10 pages, 10 sources, and then you give a 10-minute presentation to your class. However, there is some flexibility with that. I've been talking with your instructor. He's got some really creative ideas for you if you might be interested in doing it. That just gives you an idea of how much work is expected for this project. Now, what do you get? So, first of all, this math class becomes an honors class recorded on your transcript, right? You can take an honors class every semester. They all get recorded as honors. Secondly, you get a stipend. In this pamphlet here, it tells you how much the specific stipend is. It depends on how many credits you're registered for. If you're registered for at least 12 as a full-time student, you get a $500 stipend in exchange for completing it. Pretty good deal, right? You gotta work a lot of hours at jobs to get $500. This will be a lot more interesting than a lot of that. And so if you are interested, the first step, which I recommend you do right away, this does not commit you to anything, but the one-page sheet, that's our application into the program. That will just run a GPA check. So if you're not sure, you've taken classes at a few colleges, what your GPA is, just submit this and we'll let you know. You're not obligated to anything, then we can follow up as well. Secondly, if you are interested in completing a project, this is the application you would complete to make an appointment with your instructor to go over and to complete that project. That one's due by the 4th Friday of the semester, which is going to be February 9th this year. Does anybody have any questions for me on that? Thank you for your time, or not take up any more class time. My contact information is in this flyer, so if this isn't clear, you have any questions, let me know. I hope to see some projects from some of you. Thank you for your time.
Thank you, Dr. Leonards. And just to add to what he said, first, a student right before class asked, how do I know what my GPA is? And Beth, the answer was?
Go to your student center.
Go to the student center and you can figure out your GPA. And just from my perspective, I want to share that I did my first honors project last semester with a student. It was so fun. Like, I really enjoyed it. Like, I asked Dr. Leonards to come down here today to advertise it to you in case I could get a few more people to do it, because it was super fun for me. So obviously you should be doing it for you, but just so you know, I'll enjoy myself as well. This is a really fun project to do. So thank you.
Thank you.
Thank you for coming in. All right. Good morning, folks. Today we're going to start off with a traditional warm-up, which is these questions that I have on the board. They're conceptual review questions. So there won't necessarily be a ton of computation you have to do in your warm-up. The one rule is you just have to talk to your neighbor. You have to speak to at least one person. If you want to talk in 3 people, that's fine. you have to at least have a pair of 2. So my screen always on the board will be sign in on the attendance sheet and take any materials from the front table. I think you all already did. And then with your table buddy or someone nearby, so you can look behind you, in front of you, to the side of you, agree upon the following solutions. So read each question and come up with maybe an agreement about what you think the answer is. If you don't agree, that's fine. You might have 2 different ways of saying it, but go ahead and discuss them. So let's see, I have 1, 2, 3, 4, 5, 6 questions. You don't necessarily need to agree on all of them, but go ahead and try all of them. All right, I'm going to give you just 3 minutes to talk about these with your buddy. Go ahead.
Yeah. 880.
What does it mean to say that it was x? It means that the value of x
Ultimate mathematics is the study of statements that are either false or true, or a number. The ultimate mathematics is the study of statements that are either false or true. What is basically algebra? You can do anything as long as you do it to both sides. I'm looking at mathematical work. What are the 2 telling you? We're looking at mathematical work. What are the 2 telling? Oh, the crossing out.
Oh, yes.
I'm gonna do this.
You have to
I don't know, but my lowest grade was a B last semester.
I was like OBs, I had 1 C and something 2.5.
I don't know if I should do this right now. I don't have or blue.
Oh, thank you. I was about to say, you said out your name 10. Thank you very much.
So who would we turn this into, Mr. Kevin?
Me. Yeah, I'd work with you on that. All right, folks. Go ahead and wrap up your conversations. Let's review as a group. To practice your names, I'll just be calling on some of you at random. So approximately when was the technology of algebra written down for the first time ever? Let's see here, Brandon?
It was around 800 AD.
Yeah, it's right around 800 AD. I think the date on the book was 820 AD, but 800 AD. So 1,200 years ago is how long we've had the technology of algebra. How about the next one? In order for a math problem to be algebra, what 2 symbols do you need to see in the math problem? How about Feza? What 2 symbols do you need? You need an equal sign and an x. You need a variable and an x. That's what makes it algebra. All right, thank you very much. What does it mean to say that x equals 5 in the equation 2x minus 7 equals 3? First of all, does it? Well, I guess that's the question. What does it mean to say x equals 5 in the equation 2x minus? Yes, Rico. Exactly, it makes it true. If you take the 5 and you plug it into 2x minus 7, it should make the equation true. And just to confirm that, 2x minus 7 equals 3, and then I'll put 2 times 5 minus 7 equals 3, and then that's 10 minus 7 equals 3, and then that's 3 equals 3. This right here is the magic moment that ends every algebra problem, a true statement. So anytime you do an algebra problem, the solution is not, well, the end of the problem is not saying x equals 5. That's not the end of the problem. The end of the problem is a true statement. So as soon as you get to a true statement, you say, yes, okay, I got it. That's the solution to the problem. Okay, thank you, Rico. Ultimately, mathematics is the study of statements that are either, what?
True or false?
Yeah, true or false. That's what we're ultimately studying. That's what we're looking for at the end of every problem is a true statement or a false statement. Hopefully a true statement, because that means you got it right. If it's a false statement, what do you need to do?
Right.
Yeah, you got to go back and find a mistake and see if you can find your mistakes. Okay, what is the basic rule of algebra? The basic rule of algebra. I started it off. Rico, I love your enthusiasm, but I'm going to call on somebody else. Amber, what is the basic rule of algebra? You can do anything you want, as long as you do it to the other side. As long as you do it to both sides, right, folks? You have to do it to both sides. So when I have the equation 2x minus 7 equals 3, and I want to move that 7 to the right, I have to cancel it by adding 7, and I have to do it to both sides. And that way it cancels, and I get 2x equals 10. And again, to get rid of the 2, I have to divide it, but I have to divide it from both sides. And that's how I get x equals 5. What I see all too often is that people, well, not everybody, but some people, will just show it on one side. In fact, normally they just show it on the other side. In their head, they're like, okay, I'm adding 7, so they put it over here, and they only show it on one side. That's just not a best practice. It's a little sloppy. You really need to show it on both sides for it to be algebra. That's what I'll be looking for to give you full credit on a test. Okay, last question. When looking at mathematical work, what are the 2 telltale signs that you are actually looking at algebra? So what do you need to see in algebraic work? For instance, I claim that is algebraic work right here. What is it about that makes it algebraic work? How about, oh wait, did you want to do it, Elva? What? Did you start talking?
Yeah, I can say it.
Yeah, go ahead, tell us.
It's just cancellation and then the x equals 5.
Absolutely, it shows the cancellation lines. You have to see cancellation lines for it to be algebra. The x equals 5, yeah, that'll be at the end. But there's one other thing that you need to see.
The action.
The what?
The action steps.
The action steps, exactly right. You need to see 2 action steps on both the left and the right, and then 2 action steps on both the left and the right. So those are the 2 telltale signs that it's actually algebra. You will see action steps on both sides, and you'll see cancellation lines every single time. And in fact, what it will look like, it'll go equation, action step, equation, action step, equation, and it just keeps going like that. Equation, action step, equation, action step, equation, action step. Okay, wonderful, folks. That's just a little conceptual review at the start of class. Today, what are we doing? Well, today is January 22nd. We're going to be covering sections 5.1 through 5.3. I don't have any notes in particular, but I do have a joke for you. So, we did the pirate joke last time, right? Okay, so if you have 5 apples in one hand and 7 apples in the other hand, what do you have? Really big hands! Right? Okay, well, that's it. All right. So today, I'd like to just do some concluding thoughts on that algebra overview we were doing the other day. And then we're going to review the syllabus quiz. I am assuming everyone brought back their syllabus quiz, so we'll review the answers. We'll take a look at my math lab, because I know that a lot of you have signed up or are about to sign up and maybe have some questions. And we'll begin chapter 5. So the algebra overview that we were doing yesterday, unfortunately, I can't budget any more time to do it today, but we covered the main ideas really yesterday. So we don't have time to finish the rest, but I will post a full solutions guide to the rest of the packet. So I'll go home, I'll fill out the rest of it, and then I'll post it under announcements, just in case you're curious and you'd like to go online and check out what the rest of it was. Okay? I believe it'd be well worth your time to check it out, but it's not a requirement by any means. It was really just an introduction so we could get at the philosophy and the history behind algebra. Okay, the syllabus quiz. I will continue practicing your names by calling on people. So let's hear the answers. The very first one. I need to bring a blank to every class. Rob?
I could a graphic or scientific calculator, textbook, table, notes, and pencil.
Oh, well, wonderful. That's a very thorough answer. I was looking for a calculator, but all those things are very important, right? So you need some sort of a scientific calculator. Thank you, Rob. By the first week of class, I need to purchase online access to what, Jonathan?
My math lab.
My math lab, exactly right. You need that for the course. All right, next, 5% notes packet. The packet is worth 10 points, and I will lose what for every problem blank or incompletely solved? John?
10 points.
You know, 1 point. It's only worth 10 points. You lose a point for every problem you don't do. 5% midway quiz is on my honor. I must complete it on my own. I can use blank, but I cannot use blank. Kylie, what can you use?
Book and notes.
You can use your book and notes. What can you use?
Other humans or Google.
Other humans or Google. Very good. You can't look it up
I
online.
do it like
Or what, Junior?
I just like
Oh, okay. So, 5% practice test. The practice test is worth 10 points, and I will lose blank for every question I leave blank. No, what's your name? I don't see your name, Tent.
Oh,
What's your name again?
Sino.
Sino. what will you lose?
1 point.
Yeah, 1 point for every problem that's blank. 25% online My Math Lab homework due on the day of the test. If incomplete, I can continue working on the remaining problems for what? Oscar. Okay. But you can continue working for more than a day. Yeah. April? Yeah, 30% deduction. So you'll still get full credits for the problems you already did. But for any problems that you're doing late after the due date, I'll give you credit for it, but minus 30% on just those problems. Thank you. 40% test. If I have an emergency or sickness on the day of a test, I must email Mr. G blank in order to take the test at the testing center within 3 days. You need to, Isis? Yeah, before class. Has to be before class, folks. Just shoot me an email. All right, final exam. I will keep all of my blank and review them before our exam. Carla.
I put notes packets, and my midway quizzes.
Yeah, notes packets, midway quizzes, and especially your tests. You definitely want to review your tests because essentially the final exam is accumulation of all those test questions. Okay, great. Attendance. I will sign in and be in my seat at the start of class, which is at what time? Let's see here. Sienna. Yeah, 8 o'clock, right? And I am allowed up to 2 tardies for free. Starting on the 3rd tardy, I'll lose what from my final course grade? Erica.
Oh, 1%.
Yeah, 1%. I think the next question is the same. I'm allowed up to 2 absences for free. Starting with the 3rd absence, I'll lose what from my grade? Siobhan. Wait, Siobhan? Siobhan, okay, great. 1%, yep. I can be absent a maximum of 5 times, excused or unexcused. On my 6th absence, I will be what? Seraphine. Yeah, withdrawn from the class. Required office hours. Before the day of what? I will come to office hours for a 5 to 10 minute chat to review my homework. If not, I'll lose what from my first test grade? Oh, how about Megan? Before the
question.
First exam?
Yeah, before the day of the first exam, right?
50%.
Yeah, you lose 50% of the first exam. Now, folks, I don't want to take 50% off of any of your exam grades. That's a scare tactic, right? That's just my way of making sure that you actually come in and visit with me. Any of you could do that right after class today. I'll go right to my office. You can come on in. It's really a 2-minute chat. I just look at your notes and then you go. Okay. If I earn less than blank on any quiz or test, Mr. G will record my grade as a blank until I come into office hours to review the test. And after that, I'll put in the grade you earned. Beth?
70%,
Yeah, anything less than a 70.
and the grade as 0.
Yeah, I'll put the grade as a 0 in the grade book. Now, again, folks, this is just a scare tactic. I don't want you to keep a 0 for the test. I want you to earn the grade that you earned, but you have to come in and review with me to actually get the grade. Okay, signature? Well, I have no idea what you wrote. But that's it, folks. So during our 10-minute break, if you would, as you all leave the room to take a break, you can just bring your student information sheet and your syllabus quiz right up here and drop them off. Rob?
Here's one of the questions.
I did. Which one?
The extra credit one, just above the office hours. I want to know that.
Oh, I can earn extra credit for perfect attendance. If I have 0 tardies, I will earn how many bonus points, Rob?
5.
Yeah, 5 bonus points on the final, and 5 0 absences. I'll earn 5 more bonus points. By the way, 10 bonus points on the final exam is worth 5% of your final exam. Again, good attendance and no tardies. If you had an 87% on the exam, you would bump up to a 92% on the exam. So that's a very generous extra credit on the final exam. That's worth 5%. All right, super duper, folks. So you'll turn all that in during the break. Yep. Now let's take a look at my math lab. So everyone, just so you know, just in case you're still waiting on either financial aid or your next paycheck, either way, you can still go to my math lab and sign up anyway. So here's what I'm going to do first. When you go to your Canvas course for us, you can click on the syllabus. And when you download and look at the syllabus, you go to the very last page. The very last page has the instructions to get on my math lab. So then you would go to pearson.com/mylab. So I'm going to do that. www.pearson.com/mylab. So here we are. And right here, you can see it says register. So I'm going to go ahead and register as a student. And it says, you may be having issues. No, just continue. All right. And now what do? You need your email address, your instructor's course ID, and an access code, credit card, or PayPal. And so I say, OK, register now. And I would type in my course ID. That's on the instructions that I gave you. It says right here, instructor's course ID, Gabrielle 11646. So I'll go ahead and type in Gabrielle 11646, and I hit continue. Now, I need a username and a password. I don't want to just sign up a dummy account, but all I would do create account. So here I type in my email, my username, password, first name, last name, security question, and so on. And then I would click create, and then I would essentially be in. You either pay now or you pay later. You have 2 weeks to use it for free. So I can't continue this process just now. But what I could do is go back and just sign in. I hope I remember my password. Okay, so. Yeah, okay. Now, my problem. I did not memorize my password. That's a very. Oh, I didn't memorize my password. Oh no, folks, this is embarrassing. How am I going to do this? You know what? Maybe I'll do this after the break. Yep, I totally forgot my password. I have it written down. I tell you what, we're going to do this after the break. That way I can look at my password and not waste everybody's time. So we will circle back to this, and I'm going to demonstrate how to actually use the software. Okay? All right. Well, let's go ahead and proceed with our notes for Chapter 5. So we're going to start Chapter 5 today. That's what was on the calendar. Looking again at our calendar. Yeah, here we are. We're starting Chapter 5 today. We'll continue Chapter 5 on Wednesday. And that's it for Chapter 5. We're going to cover it in 2 days. And on Wednesday, actually it says today I'm going to give you your midway quiz. It's going to cover the beginning material that we did today in class. And then you can go home, use your notes, do the quiz, and bring it back next time. Okay, so here we go, folks. Chapter 5. Taking a look at the first page of Chapter 5. By the way, does everyone have this? Everybody needs a copy. Raise your hand if you need a copy. And always, please raise your hand if you need a copy. I don't want to plow forward and leave somebody behind, because I do happen to have another copy. So who needs one? Yeah? Okay. Boy, you're in luck. I have one copy. Oh, there's one person. What's your name? Jackie. Okay. All right. What does it appear, just looking at the first page of Chapter 5, what does it appear that Chapter 5 is about? Yeah, it sure looks like it's about polynomials, right? Because that's the very first thing they give you is polynomials. I'm going to attempt to write on the board with this over here. Obviously, I just failed because the first problem is up there under the bar. So I'm going to write it again right here. When we look at number 1, it certainly does look like a polynomial problem. 3a to the 4th minus 4a to the 4th plus 7a cubed plus 3a to the 4th minus 14a cubed. What's a polynomial anyway? Someone said it's a polynomial. What's a polynomial? What is it, Nathan?
One variable.
It's not necessarily more than one variable because we only have one variable. It's just the variable a. But what do you need to have, Elda?
An x is a term of a finite sum of terms of the form of axn for any real number a and any real number of n.
Now that is absolutely the definition from the textbook, and I'm going to capture the key thing you said in there. It's a sum of terms. So it's multiple terms. Poly means many, and so polynomial is many terms. So we have lots of different terms here. You'll notice, everybody, this is an a to the 4th term. This is an a to the 4th term. This is an a cubed term. That's an a to the 4th term, and that's an a cubed term. So the difference here is what the power on a is. What's really we're looking at here is the exponent. The fact that this exponent is 4 versus this exponent is 3. So what is this problem asking us to do? The instructions say combine like terms when possible. So which terms can we combine? Yeah, John?
Combine all the ones with the same exponent.
Exactly. You can combine all the terms that have the same exponent. So I'm going to underline all my a to the 4th terms. I hope you underline them as well. And I'm going to squiggle line all of my a cubed terms. And I hope you squiggle line them as well. I always use some sort of an underlining system to distinguish my terms. All right, well, we can go ahead and add together all the a to the fourth terms and add together the a cubed terms. Go ahead and do that. What would 3a to the fourth minus 4a to the fourth plus 3a to the fourth equal? Yeah, 2. 3 minus 4 is -1. -1 plus 3 is 2. So the a to the fourth terms, we get 2a to the fourth. That's combining like terms for that first one. And then combine your a cubed terms. You've got 7a cubes minus 14a cubes. How many a cubes do you have? -7a cubes. And that's the end of the problem. So it appears as though we're looking at a polynomial, which we are. We're combining like terms. But the key thing is, why can't we combine these two terms?
Different exponents.
Yeah, because they're different exponents and they represent different things. So we can't just say 2 minus 7 is -5 and 4 minus 3 and 1. That would be terribly wrong if we did that. This would be incorrect. You can't just subtract the numbers and subtract the exponents. It's not how it works. So you have to respect the different terms according to their exponents. Okay, everybody go ahead and try number 2 on your own. You can talk about it with a neighbor if you like, but go ahead and combine all the like terms for number 2. I see there was an m to the 9th term, there was an m to the 6th term, and there was a m squared term. So would someone like to share their final answer? How about John, go ahead.
I put -5 m to the second with 2, whatever, squared.
Uh-huh.
Then 9m to the 6 plus, no, -9 m to the 6 plus 9m to the 6.
Plus 9m what?
To the 6.
Okay, no, the last one. 9m to the 9.
To the 9.
Okay, is that what you said?
Oh, yeah, that's what I meant.
Okay, so let's just see here, folks. John had the -5m squared, and then he had the 6th term, which 5 minus 14 is -9m to the 6th, and then -5 plus 14 is 9m to the 9th. These are the correct combining of like terms, but we want to put this in a different order. What order should we put a polynomial in?
Biggest to smallest.
Yeah, biggest to smallest. We're going to order the exponents from biggest to smallest. So my final answer is actually going to be 9m to the 9th minus 9m to the 6th minus 5m squared. And so we always write polynomials in terms of decreasing order, in terms of the exponent, right? Okay, well, that's it. Just we're reviewing basic ideas and basic terminology. The next set of problems, identify the polynomial as monomial, binomial, trinomial, or none of these. So again, if polynomial means many terms, what does monomial mean?
One term.
One term. And binomial? 2 terms. And trinomial? 3 terms. No one really talks about 4 terms, but if you had to take a guess, what would you call a 4-termed polynomial? Maybe a quadnomial? Or think about, what do you call a quadrilateral? So maybe we'd call it a quadrinomial. Yeah, I'm just being playful. No one refers to a quadrinomial. But if you were at a math party and you said, oh, look at that quadrinomial, everybody would be like, hey, I like what you did there. Normally, you would just call it a polynomial. Okay, what would 5 terms be? Pentanomial? Yeah, and then you're probably just being silly. Okay, so, so how many terms does this first one have? How many terms does this one have?
That's just one. Polynomial.
Well, you've got 11y to the 8th, but you also have -1. Are you guys not counting the 1? Is the 1 chopped liver? The 1 is a term, and let's all identify it as such. What's the power on this y? Y to the 8th. Is there a y next to the 1?
No.
Is there? Is it maybe invisible of y to the power of 0? That's the definition. When you simply have a number, that number is actually sitting next to that variable to the power of 0. Because anything to the power of 0 is actually equal to 1. So this is just a technicality, folks, but I want you all to write it down. Anytime you have a number, like look at the next problem, that ends in the number 3, what's actually sitting there next to that number 3? Y to the power of 0. Exactly right. So going back to number 3, how many terms are there? There's 2 terms. And is it written in the correct order? Yeah, it starts with 8 and then ends in 0. So it is written in decreasing order of exponent. And so this is a what nomial? Yeah, it's a binomial. And then what about the second one? It's a trinomial. Now there's one other thing they want us to do. They want us to state the degree. What is the degree? I've given you a line there to take the note. The degree is?
8.
It's what?
8.
Yeah, for the first one, it's 8. That's correct, because it's the highest exponent on the variable. The degree is the highest exponent on the variable. Therefore, I would write degree equals 8 for that problem. What's the degree of this second polynomial? 4. So the degree would be 4. So degree equals 4. Okay. Largely what we've done thus far is just reviewed some vocabulary, terminology, making sure we all remember about exponents and how they work, and the fact that if you wanted to make a note, any variable to the power of 0 is actually just equal to 1. That's a pretty important note to remember. Anything to the power of 0 is equal to 1. If I said 5 to the power of 0, what would the answer be? 1. That's just the answer of 1. Okay, continuing on. Now, the next set, is this still on the same page?
Yes.
Right. The next section says evaluate the polynomial. What does evaluate mean? Solve. Solve is an okay word to use in this case. Solve typically means solve for x, which means you have an equation. Is this an equation?
No.
Yeah, there's no equal sign. So it's not an equation, so we're not solving anything. What does evaluate mean?
2.
What are we going to do with the 2? Plug it in, exactly. That's what evaluate means. Evaluate means plug it in. Normally, I think of the word evaluate as to mean you judge something, like I'm evaluating that pizza restaurant. It wasn't very good. But now evaluate just means plug it in. So I want us to all agree that whenever we plug in a value into a function, you're going to write it empty. Now, what do I mean, write it empty? This is 6x cubed minus 3x squared plus 5. When you write it empty, you replace every variable x with an open parenthesis. So listen to what I do. Instead of 6x cubed minus 3x squared plus 5, I write 6 parenthesis cubed minus 3 parenthesis squared plus 5. What did I do? I just replaced every x with an open parenthesis. And why did I write the open parenthesis? Yeah, so I can drop in the 2. It's a very convenient way to make sure that you're substituting, plugging in your numbers correctly. Most importantly, that's how you need to type it into your calculator. In your calculator, you would need to use those parentheses to make sure you're evaluating an expression correctly. So writing it empty is a really big deal. I'm going to say it over and over in this class. Write it empty. Anytime I say write it empty, it means you replace every variable with a parenthesis, and then you drop in the number. Okay, great. So now we actually have to evaluate that, right? We have to actually calculate it. Here's the great part. This is Math 120. 121. Yeah. You're allowed to use calculators. You're allowed to use calculators for anything you want. So on the one hand, I could sit here and we could all do this in our head, like 2 cubed. By the way, what's 2 cubed? 8. 2 times 2 times 2 is 8. So 8 times 6 is 48, and then minus 2 squared is 4 times 3 is 12, and then plus 5. 48 minus 12 is 36. 36 plus 5 is 41. So I know the answer is 41, but you don't have to do any of that in your head. You can just plug it into your calculator, okay? I don't need to see the work for that. You can plug it into your calculator and get your answer. The key thing, again, is that you're writing it empty, so when you plug it into your calculator, you're getting the right answer. And you might want to do it off the top of your head anyway, just to confirm, to make sure your calculator and your brain are giving you the same answer. Okay, so everybody go ahead and try number 6. Write it empty, plug in the -3, and either do it in your head or on your calculator, and we'll all check to see that we get the same answer. Again, if you'd like to check with your neighbor or confirm with your neighbor, I support that. This one's a little challenging because of the fact that you're substituting negatively. You have to be very careful with your negatives rules. All of your notes look really good. I can tell you're a group of professionals. So let's see here. I'm going to try this myself, and we'll all check to see if we get the same answer. 2 minus 2, something squared plus 50. We're going to drop in a -3. -3 cubed is -27 times 2 is -54. -3 squared is 9 times 2 is -18. 50. That's -72 plus 50. Did anyone get -22? Oh, goody, at least a few of you. Did anyone get anything different from -22? It's okay if you did, but you're the minority report. You might want to go back and double check your hand calculation, or go back and plug it into the calculator again and make sure you use parentheses. I'm pretty sure -22 is the right answer. How do we know for sure that -22 is the right answer? Plug it back in won't work this time because there's no equation, right? This isn't an equation. There's no equal sign, so we can't check to see if it ends in a true or false statement. So what's another way to check?
You can put equals to the original equation, equals.
Well, I suppose you could put an equal sign to the original and say equals -22 and then try plugging it back in again. Yeah, okay, Beth, Blake, that kind of works. You could turn it into an equation. How else do we know we're right? Well, you could check with a buddy, but could you and your buddy both be wrong? Maybe. So how else could you check?
Calculate.
You could check a calculator for sure, or you could. Yeah, the answer is in the back, right? We've got the answer key on the back page, so you can always flip to the back and check to make sure. Now, how do you know the answer key is right? Oh, well, now we're philosophically in dangerous waters. I don't know. We assume the answer key is correct. All right, very nice, folks. That's what evaluate means. Next, we're going to, all right, now, folks, I'm looking at my PowerPoint and realizing that for you folks in the back, this is too small. And I goofed, and my PowerPoint is going above my ability to write. So I apologize for today. I'm going to somehow fix this so that it's projecting on the board, and maybe the print is a little bigger, because I know in the back that it's very small. All right, well, let's continue for now. This next set of questions says, perform the indicated operation. So let's start there. Perform the indicated operation. What are they asking us to do at number 7? Yeah, add, right? We've got 2 groups of terms. They're both in parentheses, and we want to add them. Well, the first thing we want to know is, what do you do with a parenthesis if the number in front of it is simply a +1? For instance, what number is sitting in front of this parenthesis?
1.
A 1, right? A +1. What's the number sitting in front of this parenthesis?
+1.
Another +1. It's invisible, but it's there. Parenthesis, when there's a +1 in front of it? You could distribute the +1. That's true, and that would be a little extra work. What you can do when there's a +1 in front of it is just drop the parentheses, right? The parentheses aren't really doing anything in that case. If there's a +1 in front of parentheses, you can just drop the parentheses. They're doing nothing. So that's a general rule. Whenever there's a +1 in front of parentheses, you can just get rid of them. So really, we're just adding all of these things together, right? The parentheses did nothing in this particular case. So go ahead and, number 7 and number 8 are both in that vein that you're just combining straight across. So again, I really recommend you come up with some sort of underlining system. Like I've got my end of the 5th terms, I'll underline. My n squared terms, I'll squiggle. And then maybe my n terms, I'll jiggy jag. That's a very technical term. And that way I can see visually what I've got. Did everyone end up with 9 end of the 5th? Minus 3, whoa.
Just 12n.
9 end of the 5th plus 12n squared. And then plus, no, plus 1n?
Yes.
Okay. Do I have to write the 1n?
No.
Or can I just write n? Yeah, I can just write n, right? Okay, everyone, I'm not going to do number 8 with you. Just circle it and make sure you go back and do that at some point on your own. Let's keep going. Number 9. How is 9 different? Yeah, now we actually have a subtraction. Okay, can we just drop the parentheses? Yeah, we cannot drop these parentheses, to be sure. Can we drop the first parentheses?
Yes.
Yeah, the first parentheses do nothing. But the second parentheses, what's the number there? That's a -1. So you can do this in one of two ways. I have a recommendation for a fast way. The technical way is, what do you do with the -1? You distribute, right? And I draw my little lines, I distribute, I distribute, I distribute, and I would multiply each term by -1 and then write down the result. Right? So I'm going to start rewriting the whole problem. I have 7x to the 5th plus 8x to the 7th minus 9 plus 9x to the 6th. And then I start multiplying by -1. So -1 times 6 is -6. -1 times 3 is -3x to the 6. And -1 times 6 is -6x to the 7. And -1 times -3 is positive 3x to the 5th. I find that method, while technically correct, a little lengthy because you have to keep saying to yourself, -1 times blank, -1 times blank, -1 times. It takes a lot of time. Whereas what you can all memorize, and what I gave you a note for up at the top, it says when subtracting a parenthesis, you must change the sign of every term inside. And that's all you do. You just change all the signs. You'll notice that's what happened. The +6 became -6, the +3 became -3, the +6 became -6, and the -3 became +3. That's very simple. Anytime you're going to distribute a negative number, you just change all the signs inside to their opposite. And that's a lot faster than constantly thinking -1 times 3, -1 times 6, and so on. That's not to say you can't do it that way. You can. It's just a little faster. All right. At this point, the problem is routine, right? We have to go through with our underlining system. I've got my x to the 5th. I've got my x to the 7th. I've got my jiggy jags x to the 6th. And I'm running out of underlines. I'm going to circle my numbers. All right. Now, I realize this problem now looks a little bit like hieroglyphics. And you might be saying to yourself, Mr. G, I can combine like terms without making my paper look like hieroglyphics. I don't have to do all that. Well, hey, proceed at your own caution, right? If you feel like you can just combine all those terms by just looking, go for it. But I find it very helpful to actually have an underlining system so that I can check and double check and make sure that I'm getting my answers correct. So let's see. And then 6x to the 6th. Is my answer correct?
Yeah, but it's not.
Yes, but no, right? Yes, it's the correct terms. That no, they're in the wrong order. What I really needed was to start with x to the 7th, x to the 6th, and then write down 10x to the 5th, and then minus 15. Okay, now is my answer correct?
Yes.
Oh, goody. Yeah, it's correct because I combined like terms correctly and I put them down in the right order of decreasing powers of x. All right, number 10, I'm also leaving for you. You can just circle that and know that you need to go back and finish that problem on your own. How does this feel so far? This is a basic review, essentially, because you've definitely done this before. I don't want to go too fast. I don't want to go too slow. And I'm trying to give you definitions as we go. All right. Number 11, a very fun word. Well, is that a word problem? It's not exactly a word problem. What is it? It's just a picture problem. What are they asking us to do? Yeah, find the perimeter. Well, folks, perimeter is one of my favorite etymologies. So a quick side note. What does etymology mean? Have you ever heard the word etymology? What does it mean? If I said, what is the etymology of perimeter?
Definition?
Yeah, well, it does mean kind of the definition. And you're right, etymology is the study of something, because ology means study of, whatever etym is. But what is the etymology of perimeter? It's the root of the word. Historically, where did this word come from? And historically, it came from Greek, perimetros. I'm not writing in the Greek alphabet, but it came from the Greek perimetros. What does the word peri mean, and what does the word metros mean? Maybe you can take a guess about metros. Metros sounds a lot like metric, which refers to the metric system. And what do you do with the metric system? You measure things, right? So metros means to measure. Now, what about peri? Are there any other words you know that start with peri? Other than Perrier, which is water, that doesn't count.
Perimeter?
Well, perimeter, absolutely. I mean, we're looking at the word perimeter. Is there another word that starts with peri? Maybe if you've seen the Hunt for Red October or any good submarine movie?
Periscope.
A periscope, exactly. In a periscope, you pop up the periscope, and what do you do with the periscope? You look around. Exactly. Peri means around. So looking at the etymology of the word perimeter, perimetros, what does perimeter mean? To measure around something. And that's exactly what perimeter is. You take your triangle, and how are we going to find the perimeter? Well, let me do an easy example. What if the sides were 3, 2, and 5? What would the perimeter be?
10.
10, right? You just add them all together. That's the etymology of perimeter, to measure around something. By the way, what's the etymology of etymology? Etymology. What does ology mean? Study of, right? This is really cool, study of. What does etym mean? I don't know any other words that start with etym, so I'm just going to tell you. Etym essentially means truth or true meaning. So what does etymology mean? The study of what is true. Isn't that deep? Why would you want to study anything else, right? Other than the study of what is true. So that's the etymology of etymology and perimeter. And that's just to help you remember, because a lot of people switch perimeter and area. You get a perimeter or area problem and you calculate the other one. I need you all to remember, perimeter means you add them all together. So what do we do with that problem number 11? Okay. Just add them all together, right? I'm not going to do it with you. You circle it, you can do it on your own. Because it's like what we just did. Now, I'm not trying to load you up with problems to do, but I'm trying to focus our time in class together on new ideas. And I feel like we've already essentially done a problem like number 11. Although I'll go ahead and ask you, in number 11, if you do start by using parentheses, do you need to keep the parentheses? No, you don't, because you're just adding everything together. Okay, very good, folks. We're looking at section 5.2 now. That was it for 5.1. 5.1 was talking about combining like terms, and we were noticing the fact that terms are different when the exponents are different. So we now want to really focus on exponents. What are exponents? What is an exponent?
The numbers on the top.
That's true. The little number on top. I heard someone else say the power of love. No. What is an exponent? We know it's the little number up top. And we often say x to the power of 5. But what does it do?
Multiply.
Yeah, you're multiplying something by itself how many times? That many times, right? So when using exponents, an exponent means repeated multiplication. That's it. It's just repeated multiplication. If somebody came up to you on the street and said, define exponent, you could be like, repeated multiplication. And that'd be it. So how do I rewrite number 12 using exponents? Yeah, just x to the 5th, right? That's it. By the way, folks, these little lines over here, I'm not too concerned about you writing your final answer over there. If you like to do that because it looks neat and tidy, you can. But you can just write the answer next to the problem, and that's okay too. Okay, how do I write down number 13 using exponents? No, I'm going to start calling on people. How about Jonathan? How do I write number 13 using exponents?
My guess would be parentheses b plus c to the 3rd power.
Yeah, to the 3rd, exactly right. And then Sienna, how would I write number 14 using exponents? You can give it a shot. I already started you. 1 over. Yeah, what did you say? Yeah, 5 to the 4th. That's exactly right. 1 over 5 to the 4th. And how would we write number 15 using exponents, Siobhan?
-7x to the 4th.
Exactly right. And how would you write number 16 using exponents? I can't. No. How would you write number 16 using exponents? Yeah, 1/2 the power of 6. Yeah, exactly right. Okay, so that's it for an exponent. Of course, this begs the question, doesn't it? Can an exponent only be a whole number?
No.
Right? Because repeated multiplication, what if the exponent was 3.5? How do you multiply x times itself 3.5 times? You'd be like x times x times x times x. Right? What does that even mean? Can it be not a whole number? What else could it be other than not a whole number?
Fraction.
Yeah, it could be a fraction. Can you do it a fractional number of times? X to the 1/2. Can you just multiply x times itself just half a time? Yeah, I'm drawing half of an x to be silly. What could it be beside a fraction or a decimal? Can an exponent be?
Maybe like pi.
Yeah, could it be like pi? X to the pi. Sure, you can. What else could the exponent be? We already saw one interesting example today.
Letter?
Well, that's true. It could be just a letter. What about x to the 0? Can it be 0? Yeah, because that's just equal to 1, right? What else could the exponent be? We've covered fractions, decimals, variables, 0. Negative, exactly. Could that be negative? What does that even mean? To multiply x times itself negative 3 times. Are all of these legitimate exponents that we can solve? Yes, and in fact, that's what we're about to solve together. Our break is at 9, right?
Yeah.
Okay, I think so. Okay, right. So yes, it is in fact, you are able to raise anything to an exponent of anything, and that's just fine. So let's go ahead and switch over now. I gave you a little interlude packet. It's the packet that says Understanding Exponent Rules. I'm calling this an interlude. What's an interlude? Maybe you've heard of the word interlude, like in a movie, if it's a really long movie, there's an interlude. Or if you go to a symphony or an orchestra, there's a little break in the middle called an interlude. Have you heard this word, interlude?
It cuts in the middle.
What?
It cuts like in the middle.
Yeah, it kind of takes a break from what you're doing and you do something else real quick. I wonder what the etymology of interlude is. I have no idea. I've never looked it up. Sienna, do you know? You don't? Oh, uh-oh. I don't see any more over here. Sienna, I don't think I have any extras. Does anyone have an extra? Maybe someone the other day accidentally picked up. Oh, no, it was today. Did someone accidentally pick up 2? Sienna, I'm very sorry. For the time being, maybe you can look at Erica's work and write it down on a sheet of lined paper. Yeah, sorry. I'll print more next time, just in case. All right. So this is my little interlude. We're going to explore exponents. And we're going to see how it is, in fact, possible to raise an exponent to something that is not a whole number. So first of all, we already know that an exponent simply means, well, what, Elder? An exponent means? Yeah, repeated multiplication. Yes, wonderful, thank you. So you all know what 2 to the 5th means and x to the 4th means. Now, I gave you this whole row of numbers here because it's helpful to practice your powers. This might sound super geeky, but when I'm standing in line or super bored somewhere and I need something to do, I'll start doing powers of 2, right? So on your own paper, you could go ahead and jot down 2 to the power of 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th, 8 times 2 would be 16. 2 to the 5th, 16 times 2 is 32. 2 to the 6th, 64. Times 2 again, 128. Times 2 again, 256. Times 2 again. That'd be 512 times 2 again. That's 1024. Now, so the super fun part is I challenge you to try this when you're standing in line somewhere. You can even count on your fingers. Be like 2, 4, 8, 16, 32, 64, 128, 256, 256, 512, 1,024, 2,048, 4,096, 8,192. You just keep going. You're just practicing multiplying by 2. The key thing is you want to be familiar with these numbers. You want to recognize them on sight. Like if you were walking down the street and you saw a criminal and you're like, oh my gosh, I recognize that man. Well, I would want you to recognize these numbers. If you ever see the number 256, I want it to tickle your brain and be like, hey, that's a power of 2. So I want you to be familiar with these. Powers of 3, not so much. I mean, you do see them. 3 to the 1 is 3. 3 squared is 9, 27, 81. That's about as far as you really need in most math classes. You just need to be able to recognize those numbers. If you ever see 81, you should be like, hey, I recognize that number. That's a power of 3. Likewise for 5, you definitely want to recognize your powers of 5, 25, 125, and 625. Definitely, you should be able to recognize those that far. Powers of 10, I think you'll all recognize. Right? What do powers of 10 look like? How many zeros are there in any power of 10? Yeah, whatever the exponent is, right? 10 to the 4th, that means you have 4 zeros. 10 to the 5th, that means you have 5 zeros. So I give this to you because it is important that you start recognizing numbers like friends. I should have said friend, not criminal. I don't know what I was thinking. You see a friend on the street from years ago, you'd be like, hey, I recognize that person. So that's just a thought for the first page. Turn the page. Now, I do need to be able to fit this on the screen so I can actually do it with you. Ah, there we go. All right. I've got them all up there, from 2 to the 5th down to 2 to the negative 5th. We're going to do a little experiment together and discover for ourselves what anything to the power of 0 is and what negative exponents mean. Maybe you've done this before, maybe you haven't, but it's a really fun exercise. Which of these problems can you already calculate?
2 to 0.
Yeah, well, let's pretend we don't know 2 to the 0. Let's play ignorant for a second. Which one's can we definitely calculate? Yeah, 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th, and 2 to the 5th. Those are easy. We definitely know that. Exponent means repeated multiplication. We've got those. Now, what pattern are we noticing? Let's work upward, shall we? What are we doing every time we move up from one number to the next? Yeah, multiply by 2. Put some arrows. Show that as you go up each step, you multiply by 2. You go up a step, you multiply by 2. You go up a step, you multiply by 2. It's just a pattern we notice. What's the pattern on the left-hand side? Look at the exponent. What's happening to the exponents? You're adding 1, right? Draw some more arrows. On the left-hand side, we're showing the pattern of what happens to the exponent. I'm adding 1 to the exponent. I'm adding 1 to the exponent. So this begs the question, we know how to go up. What happens if we go down, right? So how do I start again at 2 to the 1st? How do I go down on the exponent side?
Subtracting.
You're subtracting 1, right? So then you go down and you subtract 1 again, and you go down, you subtract 1 again, you go down, you subtract 1 again, and go down, and you keep on subtracting. So the left-hand side, we're noticing what's happening to the exponent. What's happening on the right-hand side? How are we going down every time? Yeah, we're actually dividing by 2. Sorry, maybe that's what we should have written first. So to go from 32 down to 16, we divide by 2. From 16 down to 8, we divide by 2. From 8 down to 4, we divide by 2. From 4 down to 2, we divide by 2. So obviously, what would we do?
Divide by 2.
We'll divide by 2. And so 2 divided by 2 is 1. And that's why anything to the power of 0 is equal to 1. So that's a nice little demonstration so you memorize it for the rest of your life. Now, what happens if I go again? Should I keep dividing by 2? Yeah, of course. That's the pattern. We're dividing by 2. So what's 1 divided by 2?
-2.
Not negative 2.
2.
Not 2 either. What's 1 divided by 2? You could all type it into your calculator. Yeah, 1/2. You could say 0.5, but fractions are better. 1/2. So everyone go ahead and write down 1/2. Now here's the exciting part. What happens if we go again? What's 1/2 divided by 2? 1/2 divided by 2.
1/4.
It's 1/4. Just in case you need to see it, when you divide by something, you multiply by the reciprocal, right? So 1/2 divided by 2 is the same as 1/2 times 1/2, and that's definitely a 1/4. So now this next answer is 1/4. Notice we now have the answer of 2 to the power of -1 and 2 to the power of -2. What would the answer be for 2 to the power of -3?
1/8.
1/8. And the power 2 to the -4th?
1/16.
1/16. And 2 to the -5th? 1/32. We're now in a position to answer those first two questions. What happens when an exponent is equal to 0? The answer is 1. And then what happens when the exponent is negative? Well, you do divide, but what happens when the exponent is negative? What do you do to the answer?
You invert it.
Yeah, you invert it, and the word for that, for inversion of a fraction, is called
Reciprocal.
reciprocal, right? You take the reciprocal. So up there in your notes, what happens when an exponent is negative? You take the reciprocal. When I say take the reciprocal, you could say you flip it. You could say you make a unit fraction, 1 over the number. But you take the reciprocal. I think that's a real good definition. You take the reciprocal. So for instance, 5 to the power of 2 is what? 25. 5 to the power of -2 is 1/25. Exactly right. So a negative exponent just means take the reciprocal. Perfect timing. So everybody dance now, but really everybody get up now. And again, I really recommend you leave the room. Come back, but leave the room and get yourself a drink of water and use the restroom and take a walk outside. It's a lovely day. Everybody be back in 10 minutes. Actually, it's 9 o'clock. Be back in the room at 9:09 so that we can start promptly.
And you want these.
Oh yeah. Well, whether you bring it up to me now, your syllabus quiz and your personal information sheet, or at the end of class, either way, I want those. We can make 2 piles right here. Thank you, Carl. We're gonna start with you. Bam. There we go. Thank you, folks.
Do you have, by any chance, an extra sheet of the syllabus quiz? Because I never got one.
Boom.
Thank you.
Somebody else had it. Thank you, Jonathan. Thank you, Rico.
Hi, sis. Does anyone ever just say, hi, sis? That sounds like hi, sis, like hi, sister. But yeah, hi, ISIS. You really have to distinguish that.
Did you not have this one? Oh, okay. Thank you, Feza. Thank you, Andrea. Andrea, right? No, is it Andrea or Andrea? Andrea. Say it again.
Andrea.
Andrea. Okay, thank you. Gosh, it's halfway. Thank you, Mama.
Have you tried pushing it down? So it's yeah.
Yeah, I mean, I could always try again. I did try fiddling around with it. Yeah, it's very hard.
It doesn't have the actual little arrows to move the screen.
I don't believe so. If you, I don't like this is just changing the width and all that, but I don't see it in terms of dipping. No. And yeah, they have it screwed on tight, so I don't think I could. You know,
From the top though?
no. Please be very careful. Yeah. Yeah, I can rotate it from that.
Is there a little leg on the
There is a leg, but the problem is that they have it screwed. They screwed the projector onto this metal thing. So even if I could adjust the legs.
Well, you can move basically here.
What? Right. Yes, Andy. Okay, is it working?
Yes, sir. No, hold on, let's move where you're standing. This is very dangerous.
Is it actually rotating?
Yeah, yeah.
You're
Yeah, it's
kidding.
going down.
OMG. Oh, this is so exciting. Thank you. Keep going. Now all I have to do is do that every single day.
No, you won't.
Well, other people use this classroom.
Yeah, but they don't know how to do it.
Right. But they would call in a facilities request to fix it. Hey, that's great. Thank you. What did you do?
If you look on top, you can see
Where is it?
right there. Yeah, that's one that'll move forward. There's two in the back that are supposed to kick it back up.
Okay. Sweet. Thank you. Wow, I didn't realize that could work. Yeah, I wish everybody in the world was okay with that, but I think other people won't. Thanks, Mike. Having that solution is almost worth standing there and rotating that little knob. Oh, okay, I see it now. Oh, so that's it. You just did the one in front?
No, so yeah, so there's two in the back as well. You also have to loosen them up so it can have the little clearance.
Oh, I see. Loosen the ones in the back. So all I really need to do now is just change the one in the front. Because it's
no, because now the ones in the back they're extra long, so you'd have to loosen those. I mean, you'd have to get this pushing back down now.
Sweet. Oh man, I'm so excited. Yeah.
You also have one you do one side and figure it out.
All right. Done. Oh, you found it. Great.
Thank you.
Sure. Oh, great. Thank you.
Did you get the definition of reasons?
Mr. G?
Yes.
The homework problems, are they the same, problems that are in the book itself? Or are they different?
For my math lab?
Yeah.
I did assign those problems by looking at problems in the book and putting those in my math lab. So
Okay.
yes, you'll want to see, I think you can click on it somehow to see what number it's actually referring to. So yeah, I mean, see like chapter 5, I think the problems will just say 1 through 80 or whatever. So it's not 1 through 80 from the textbook. But if you click on each problem, I think it'll actually say what problem it is from the book.
Okay.
So, yeah.
Well, I happen to have the book because I started this class.
Yeah.
So I have the book, so I
Okay.
was just wondering.
Yeah, and no matter what, you should be able to just look at the problem from my math lab and just look at it and then go to the textbook and find where that problem came from.
Okay.
Yeah.
All right, thank you.
You're welcome. All right, folks, everyone is here. Let's keep going. We've successfully answered the question, can an exponent be 0? And the answer is yes. Can an exponent be negative? And the answer is yes. So what if the exponent is a fraction? So everyone turn the page. And question number 3 is, what happens when an exponent is a fraction? Well, I don't necessarily have a proof for you about why this is so. I'm just going to offer you the definition. And I'd like to challenge you to see if you can come up with a proof of why this is. But by definition, x to the power of 1/2, okay, any number to the power of 1/2, that is definitionally the same as the square root of x. So when you square root a number, you're actually raising that number to the power of 1/2. So in my examples here, 4 to the 1/2 is really the square root of 4, which is 2. And 9 to the 1/2 is really the square root of 9, which is 3. And x to the 1/2 is just the square root of x. So folks, that's the definition. Again, you can prove it for yourself, but I'll leave it as a challenge. So question 4, what happens when an exponent is any other unit fraction? What is that word? Unit fraction. What's a unit fraction? In ancient Egypt, they used fractions rather than decimals. The decimal system came much later. But they only used unit fractions. So they only used the fractions 1/2, 1/3, 1/4, 1/5, 1/6, and so on. What's a unit fraction? You know, 1 over something. Unit refers to the number 1. The number 1 is the unit. It's the counting unit. So a unit fraction is anytime you have a numerator of 1. And so what happens when an exponent is any other unit fraction, like 1/3? Well, x to the 1/3 is definitionally the same as the cube root of x. What is x to the power of 1/4?
So 4.
Yeah, the fourth root of x. So you can do more than just square roots. And by the way, what's the little number right there for a square root? There's a little invisible number right there. You just don't see it. A 2, because it's a square root. This is a cube root, so there's a little 3. That's a fourth root, there's a little 4. What would x to the power of 1/5 be? The fifth root of x. Now, you may or may not have studied these types of roots before, but I'll just give you a quick example. We all know that the square root of 25 is what? 5. And why is that? Because, all right, because 5 squared equals 25. That's how you would say that. The square root of 25 is 5 because 5 squared is 25. So what would the cube root of 8 be? The cube root of 8. What times itself 3 times would equal 8? 2. Because 2 cubed equals 8. So that's what we mean when we do some sort of root other than a square root. A square root, there's a little invisible 2 there, but we never write it because we all assume. We know it's a square root, meaning what number times itself twice would equal that number. So cube root, fourth root, it follows the same rules. So what is 8 to the power of 1/3 really? The cube root of 8, which is 2. What's the 16 to the power of 1/4? That's the fourth root of 16, which, yes, is 2. And then what's 32 to the 1/5? The 2. Well, that's true. The answer is 2. But what's the definition? The fifth root of 32. And then you'd have to sit there and ask yourself, what times itself 5 times would equal 32? And the answer is 2. Because 2 times 2 times 2 times 2 times 2 is 32. So that's what happens if you raise an exponent of a unit fraction. It simply means a root. That's a nice definition. So in general, a unit fraction exponent is simply a root. Okay, question number 5. What happens when an exponent is a regular fraction? Like not a unit fraction, but the type of fractions we use all the time. You know, like 2/3 or 4/5. How do we do that? Any guesses? Wild guesses?
Cross multiply.
Cross multiply somehow? Well, I did write down 2 fractions next to each other, so that would apply cross multiplying. What if it's just one fraction? So for instance, everyone write down x to the power of 2/3. What we have there is 2 pieces of information. What are the 2 pieces of information in a fraction?
The numerator.
The numerator and the denominator. We already know what the denominator is. What does the denominator represent?
The whole.
It represents the root. So everyone draw a little line and label that. The denominator is the root. Denominator is the root. So what would the numerator be? This seems tricky, but it's actually not tricky at all. What? It's what? What go? Oh, well, that's true. It does go inside the root. Here's an example to make it clear to you. What's the power? Well, hold on. What is 5 to the power of 2 again?
25.
25. What's 5 to the power of 2 over 1?
25.
Still just 25, right? Does the 1 do anything?
No.
No, it's just the denominator. 2 over 1 is still just 2. So what is the numerator?
2.
It's the actual exponent. The numerator is the actual exponent. And that's the answer here. The numerator is the actual exponent. The denominator is the root. The numerator is the exponent. So you break it down into 2 separate pieces. You say, okay, x to the power of 2/3, that's telling me 2 different things. What does the 3 tell us to do? A cube root. That's what the 3 is telling us to do. The denominator is telling you 1 piece of information. It tells you the root. What is the numerator telling you?
The actual exponent.
The actual exponent, x squared. So that's the definition. You actually break a fraction into 2 different pieces of information and write them down separately. You write down the root first, and then you write down the exponent on the inside of the root. So how would we break 8 to the power of 2/3 into those 2 separate pieces of information? You do the denominator first. So what do we write down first?
Cube root.
The cube root. And then what do I write down on the inside?
8
8 squared. Yep. So how about 16 to the 3/4? That's 2 pieces of information. Do the denominator first. So that's a what? The fourth root. And then you do the numerator? 16 cubed. Yep. Same goes for 32 to the 2/5. You break it into two pieces of information. What's the first thing you do?
The fifth root.
The 5th root, and then
32
squared. Now, here's the thing. You don't have to do it in that order, okay? You do need to treat it in two separate pieces of information, but you could go in either order. And I'd like to suggest to you that this way of doing the root first and then the exponent on the inside, it makes it a little harder because 8 squared is 64, which is a big number, and then you have to cube root 64. Had you done that in the other order, and folks, we're not going to do this, so you have a little space right here. Instead of 8 to the 2/3 being the cube root and then 8 squared, let's go backwards. We're going to do the cube root, I'm sorry, not really backwards, but we're still going to do the cube root of 8 and then raise that whole thing to the power of 2. That's just another way to see it, and I want you all to see both ways. You can cube root the 8 and then square the whole thing. This is actually better because you can cube root 8 and that makes the number smaller. What's the cube root of 8? 2. And now that's a really tiny number, and then you square it, and 2 squared is 4. So you're still splitting it into two separate pieces of information. But my recommendation would be that you do the cube root of the number, and then you put the exponent outside the root. But the fact is you can do it either way. You can put the exponent inside the root. You can put the exponent outside the root. It's up to you. So let's try 16 to the 3/4 again. You would still go ahead and do the root. So that's the 4th root of 16. But you put the exponent all the way outside, probably using parentheses. And that way, again, you can do the 4th root first to make that number smaller. What's the 4th root of 16? 2. And then you do 2 cubed, and that's 8. All right, folks. So we've talked about how to deal with exponents that are whole numbers, 0, negative numbers, unit fractions, and fractions. We're not going to do number 6. That gets us more into logarithms, which this class doesn't cover. Okay, so everyone, let's turn the page. There's a few more exponent rules that we need to know. And these are exponent rules. This is combining more than one exponent together through multiplication or division. Okay, so to do these rules, it assumes that you already feel comfortable with everything we just did, which is whole number exponents, negative exponents, 0 exponents, fractional exponents. So now let's go through these rules. You've probably seen these rules before, but then again, maybe not. The first rule is called the product rule. It states that if you have a to the power of x times a to the power of y, you actually just add the exponents, and it becomes a to the power of x plus y. That's just a formula. Let's try it. 5 to the power of 3 times 5 to the power of 2 becomes what?
5 to the power of 5.
5 to the power of 3 plus 2, which is 5, and it's 5 to the 5th. Now, that's the rule. So let's try it again. 9 to the power of 2 times 9 to the power of 6 is 9 to the power of 8, because you just add the exponents. When you multiply bases, you add the exponents. What would, this one's a little more tricky. 3 to the power of negative 4 times 3 to the power of negative 3, you still add the exponents.
3 to the negative 7.
Yeah, negative 4 plus negative 3 is negative 7. This one's kind of fun. 10 to the negative 5th times 10 to the 5th times 10 to the negative 5th. You still add the exponents.
10 to the 3.
So 10 to the power of 0, which is really just 1. Now, I don't want you just to take this on faith, that this is the product rule. We can easily see that it's true. Look at the first problem. 5 cubed times 5 squared. Well, what's 5 cubed mean? And what's 5 squared mean? And therefore, how many 5s being multiplied together?
5.
5. And that's why you add the exponents. So this is a very straightforward, common sense kind of rule. And if you just write it out, you'll quickly see why you add 3 plus 2, because that's the total number of 5s you're multiplying together. The quotient rule is just the opposite. When you divide two bases, what do you do with the exponents?
Subtraction.
You subtract top exponent minus bottom exponent. You might want to write that, top minus bottom. So in my first example here, 4 to the 7th divided by 4 to the 2, the answer would be, 4 to the 5th, because 7 minus 2 is 5. So when you divide bases, you're subtracting exponents. 8 to the power of 9 divided by 8 to the power of 4, Brendan?
That would be 8 to the power of 5.
Yeah, exactly, 8 to the power of 5. This next one's a little tricky. 7 to the power of 3 divided by 7 to the power of 5. Erica? Yes, 7 to the negative 2. And what does that actually equal? Negative exponent means reciprocal?
So 7 over, oh no, 1 over 14.
Yeah, 1 over 49.
49.
That would be the final answer, right? Because you would do 7 to the negative 2 is really 1 over 7 squared, which is 49. So 1/49 is your final answer there. And how about this last one? 10 to the 6th divided by 10 to the 6th. Yeah, maybe you obviously know that's equal to 1, right? Because anything divided by itself is equal to 1. But in this case, that's 10 to the power of 6 minus 6, which is 0, which is another proof of the fact that anything to the power of 0 is equal to 1. Because that technically means that you're dividing something by itself. All right, that's the product rule. You add the exponents. The quotient rule, you subtract the exponents. Here's the power rule. The rule is a to the power of x to the power of y. Okay, you're raising an exponent to an exponent. And what happens when you raise an exponent to another exponent? You multiply the exponents. Okay, so far we had an adding rule, a subtracting rule. Now we have a multiplying rule. So when you raise a base to an exponent and then raise it to another exponent, you multiply the exponents. So 2 cubed to the power of 2 is equal to Grace? Yeah, 2 to the 6th. Exactly right. Whoops, I wrote that wrong. 2 to the 6th. And this rule works even if the exponents are already negative. So 7 to the power of negative 3 to the power of 2. Jessica? Yeah, 7 to the power of negative 6. Which, of course, then you would reciprocal that. You would take the reciprocal. But I don't know 7 to the 6th off the top of my head. So you would just write 1 over 7 to the power of 6. That's perfectly acceptable. You don't actually have to multiply out 7 times 7 times 7 times 7 times 7 times 7. You can just say 1 over 7 to the power of 6. Okay, well, we'll finish. 4 to the power of 8 to the power of negative 5. Amber? Yeah, 4 to the power of negative 40. Which, again, you don't actually have to multiply 4 times itself 40 times, but you should take the reciprocal. And so what was the answer, Isis? Yeah, 1 over 4 to the power of 40. Exactly right. The last one's kind of fun. 10 cubed to the 1/3. 10 cubed to the 1/3. I'm going to try it out there. Kylie?
It would be 10 to the first power, just 10.
Yeah, 10 to the first power, which is simply 10. What's another way of looking at this? They do cancel each other out. If you cube something and then you cube root it, those are opposite operations. It just cancels out, and it just leaves you with the 10. Aren't exponent rules fun? These are fun. All right. There's one more, two more situations to look at. The power rule when you have multiple objects inside the parentheses. So you see you have a to the x times b to the y all being raised to the power of z. That z gets multiplied by each exponent. Okay? Just like previously we were multiplying those two exponents together, the z outside gets multiplied by both of those exponents. 5 cubed times 7 squared all to the power of 6. Who'd like to try that one? Siobhan? You're going to multiply both of those exponents times 6.
So
5 to the power of 3 times 6.
so 18.
Yep, 5 to the power of 18. Times 7 to the power of?
2 times 6. 12.
Yep, that's it. 5 to the 18 times 7 to the 12. That number is gigantic. It's super huge. It's probably in the trillions. You don't need to multiply it out and write it down. You just write it like that. Okay, another one. Beth, what about the next one?
That would be 3 to the 8
Yeah,
and 8 to the 28.
very good. Again, there's no need to multiply that out. That's a very big number. Again, probably trillions, billions, or quadrillions. Who knows? All right, that's enough. We're not going to finish those second two. How about fraction rules? Everybody, my parentheses did not show up as I expected them to. That's the fraction a over b to the power of x. So please put some parentheses in there. What happens when you raise a fraction to an exponent? Yeah, you take the exponent of the numerator and denominator separately. That's what happens when you raise a fraction to an exponent. You take the numerator to the exponent and the denominator to the exponent. So 5/3 to the power of 3. Oh, Brandon.
5/3 to the power of 3?
Yeah.
Okay. So like it'd be 5 to a third, 3 to a third.
Exactly right. And folks, that one you could multiply out, right? When you're going to be standing around in line practicing multiplying numbers, 5 times 5 times 5 is 125, and 3 times 3 times 3 is 27. So that's reasonable. You could multiply that out. If it's reasonable, you should multiply it out. If it's unreasonable in the billions or whatever, don't need to multiply it out. All right, folks, we did it. These are these are exponent rules. We're about to use all of these in practicing the homework. So that's the end of the interlude. That's the end of my interlude. That was just a quick interlude to share these exponent rules. And now we'll go back to our notes packet and continue on our merry way. Now, since I just practiced a lot of those with you, I don't think I'll do many of these with you now, because it should be relatively straightforward. But we will take the notes. So use the product rule for exponents, simplify the expression, write the answer. So the product rule states what? Same base, so a to the x times a to the y. What do?
Just multiply the exponents.
You don't
Or add
multiply the
them.
exponents. Yeah, you add the exponents. A to the x plus y. Right? Now this first one's kind of clever. Negative 9 to the 5th times negative 9 squared. What's the answer?
Negative 9 to the 7th.
Yeah, negative 9 to the 7th. The fact that it was a negative 9 doesn't change anything. Right? You keep that negative 9 because that was the object that was being multiplied by itself over and over. Okay, I'm going to leave number 18 for you. You can circle it and circle back to it. The next one, the power rules. How can we write down the power rule? We would say a to the power of x all raised to the power of y. So you're raising an exponential expression to another exponent. And now what do you do with the exponents?
Multiply.
Yeah, now you multiply them. A to the xy. What's that, Mohammed? What page number is it? Goodness gracious, are there page numbers? Page 4. All right, so 5 cubed squared is really what, Jonathan?
It's going to be 5 to the 6th power.
Yeah, 5 to the 6th. This next one is a little more sophisticated. How many objects do we have inside the parentheses?
2.
Yeah, there's 2 objects. Let's write it really nice and big and different. That's 3 to the power of what? 3 to the power of 1 times t to the power of 1, all raised to the 7th. And what do you do with that 7? Yeah, you're multiplying it by all of the exponents that are inside. So your final answer would be?
3t to the 7th.
3 to the 7th, t to the 7th. Now again, sometimes exponent rules seem arbitrary. And you're like, what, really? And it really helps to just use the definition of exponent to prove it to yourself. So for instance, 3t to the 7th is really 3t times 3t times 3t times 3t times 3t times 3t times 3t. How many 3's am I multiplying together? 7, right? So that's 3 to the power of 7. How many t's am I multiplying together? 7. So the answer is definitely 3 to the 7th, t to the 7th. No way around it. And that's why the rule is what it is. That you multiply that exponent times the ones inside. Rico, were you about to raise your hand?
So that's not the same thing as 3 teams to the 7th, though?
If you just, well, do you mean, like if you just wrote 3t to the 7th?
Yeah.
That would only be a single 3. And then t times itself 7 times. This would represent 3 t.
Okay, because
Right.
I guess I'm just grouping the 3 and the t together as one.
Yeah. You want to separate them into 2 different objects because as I showed here, technically you have a 3t times a 3t times a 3t. So there's a lot of 3's being multiplied together. How many 3's are being multiplied together? 7. Yeah. Okay, great. Well, this one works fairly similarly, but this is a little different. It's negative 2 to the 4th. Everybody rewrite this with me. They're trying to be a little tricky here. This is technically negative 1 times 2 to the 4th. All right, that negative sign is in front of the 2 to the 4th. That's not negative 2 to the 4th. If it was negative 2 to the 4th, it would be negative 2 to the 4th. But there's no parenthesis around the 2, is there? No. So this is really a negative in front of 2 to the 4th, which is really negative 1 times 2 to the 4th. And if we write this even more carefully, this is negative 1 times 2 to the 4th. And what's the exponent on the negative 1? 1, right? And if there's not an exponent, it makes it automatically a 1. So now this is really what's being raised to the power of 2. Now you might say, Mr. G, you just pulled some kung fu up there. What did you just do by adding all these parentheses? But the parentheses were necessary to distinguish what was really happening. That's a negative 2 to the 4th, which is really a negative 1 times 2 to the 4th. And that negative 1 is to the power of 1. And so now what do we do with the 2 outside? Yeah, we multiply it by both exponents on the inside. And so that gives us negative 1 to the power of 2 times 2 to the power of 8. I admit, this one's tricky. Write it all down so you have it later, and you can always revisit it again. Now, what's negative 1 squared? Yeah, negative 1 times negative 1 is positive 1, so the answer is positive. And 2 to the 8th, 2, 4, 8, 16, 32, 64, 128, 256. So the answer is just 256. Now, did it have to go that way? Well, I suppose we could have just done 2 to the 4th, 2, 4, 8, 16. And then we could have just said negative 16 squared. And then automatically, a negative times a negative would have been positive, and 16 times 16 is 256. So did I still get the answer 256? Yes. You might say, Mr. G, why did you do it that way when you could just do it this way? Well, I wanted to show you both ways. Okay, so that's the power rule. All right, now we get to do some little applications. We already talked about the etymology of perimeter. We did not talk about the etymology of what word? What are we about to do? Well, yeah, polynomial, we've said many terms.
Perimeter.
We did perimeter. We didn't do area. Area doesn't really have an exciting etymology at all, in my opinion. Area means a level piece of ground. Isn't that lame? A level piece of ground. That's what it originally refers to. That's because historically, what really mattered to people was measuring tracts of land so that they knew how much land they owned. You know, go back a couple thousand years. This is my land, that's your land. They were keeping track of who owned how much property. So area was just a level piece of ground that someone owned and had ownership of. So what does that mean we're calculating when we look at area? How much land you have. And therefore, that's why we're calculating area, the space inside the shape. Okay, so find a polynomial that represents the area. First of all, how do you calculate area? What's the formula for a rectangle? What was it? Yeah, you could do length times width. What else? Base times height. Both of those are perfectly good. So what would we say the area is here? Area equals, the base is 7x to the 5th, times the height, which is 4x squared. What do we do? What do we multiply together? Yeah, you multiply like with like. You could even rewrite it to see it better. I'm going to rewrite it as 7 times 4 times x to the 5th times x squared. I can change the order of the numbers, and that's fine. They're all just being multiplied together, so you can change the order. And now it's a little more clear. Our final answer is going to be 28 x to the 7th. Thank you, Mohammed. Number 23 works the same way. I'm not going to do it, but I will review the formula with you. What's the formula for the area of a triangle? Yeah, you can either say base times height divided by 2, or you could say 1/2 base times height. Either formula works just fine. So I'm going to leave number 23 for you. You're ultimately just going to multiply them together in the same way. Now, you might be thinking, what's 5 times 3 times 1/2? What's 1/2 times 5 times 3? Well, what's 5 times 3? $15. What's half of $15?
7.5.
750. So the answer would be 7.5 something, right? So it's easy to multiply by fractions. You can either do it in your head, think of money, or you can do it on your calculator, and that's just fine. Okay. Oh boy, section 5.3. Here we are, folks. We're moving along. So those are your exponent rules. Boy, I hope that my computer has not been this fuzzy the whole time. Okay, there you go. All right. This is our last section for the day, 5.3. And this section is all about distributing. Distributing. How do we normally use the word distributing in everyday life? Like maybe a distributor, someone who distributes things, like a shipping company or a freight company. They distribute things around the world. What do we mean when we say distributing in mathematics?
Multiply.
Multiplying. Yeah. And what did you say, Fezza? Yeah, multiplying across? Yeah, absolutely. Remember, distributing means multiplication. Fundamentally, distributing is multiplication. It means you're multiplying. Now, when you distribute a positive number, like we're about to do right here in number 24, when you distribute a positive number, well, you can go ahead and do all the multiplication in your head and say 9 times -2 is -18, and 9 times 1 is 9. Well, what do you notice about the signs?
They stay the same.
They stay the same. When you distribute a positive number, all the signs inside the parentheses stay the same. So when you distribute a positive number, all signs inside stay the same. And see, that's the shortcut. This is a glorious shortcut. You don't have to sit there and actually do 9 times -2 is -18, 9 times positive. That's not. You don't have to think about every single one using your negatives rules. You just keep the signs the same. You're like, okay, that's negative plus, that's negative plus. And you don't have to use your brain power to be thinking negative times negative is positive, positive times negative. You don't have to do all that. Okay, what about when you distribute a negative? What happens?
Signs.
All the signs change. They change to their opposite. When you distribute a negative number, all signs change. That is, plus becomes minus and minus becomes plus. Again, super easy. You're no longer using your brain power to think a negative times positive is negative. No, you just change all the signs. So right now, I'm going to go ahead and just look at the signs. What are they? Negative, so my answer is going to be positive, positive. I don't even have to think about it. So now all I have to do is actually multiply. So this is still a challenging problem, but at least I know what the signs are going to be. The signs are going to be a positive number followed by another positive number. So what's 12 times 10? 120. But what's x to the 7th times x to the what? What's x to the what? X to the 1. What's x to the 7 times x to the 1?
X to the 7.
X to the 8, right? You add the exponents. So that'll be 120 x to the 8. And then we do the second one, 12 times 7, 84. Which is 84. And there is no x term right there. So the answer would just be x to the 7th. So it's 84 x to the 7th. Now, folks, if you wanted to be technical, negative 12x to the 7th times negative 10x minus 7, there is a variable right here. There is a variable right there. It's invisible. What is it? X to the power of 0, right? Because x to the power of 0 is equal to 1. It's technically invisible. And therefore, what's x to the 7th times x to the 0? X to the 7th, because 7 plus 0 is 7. So I'm just throwing in that detail. You don't have to constantly think about that, but I'm just pointing out that when you don't have an x term, you keep the x term that was out front. Okay, very nice. So that's basic distributing. How many parts of your brain do you have to use? You have to multiply the numbers, you have to multiply the signs, and you have to multiply the exponents. How many brains do you need? 3. At least 3 brains to do this problem. You need to think about 3 different details, one at a time, to be very careful. Okay. Number 26, I'll leave for you. We're going to turn the page. Okay, great. Now we get to something a little more exciting. Number 27. What's happening there?
You multiply the numbers to each one.
Yeah, we're going to do a lot of multiplication. How do we do it? How do we do the multiplication? And first of all, what's that first polynomial called? It's a binomial, because there's 2 terms. What's the second polynomial called? Trinomial. If you were just to take a guess, how many terms will the resulting polynomial have? Will it be another trinomial? Will it be a binomial? Will it be a quadrinomial? Will it be a pentamial? I don't know. Maybe we can't really predict it just yet. But just to think about it, we're about to multiply a whole bunch of terms and then combine a lot of terms, and we're going to end up with another polynomial. Are we going to end up with a monomial? A single term? No. Chances are very unlikely, right? We have a lot of different exponent terms here. We're not going to end up with a monomial. That's too few. Okay, so let's try it, folks. What do we do? We do what? Ah, thank you for saying that, Rico. We are now doing something fundamentally different. We're multiplying. We are now multiplying two parenthetical expressions together. We have to keep the parentheses. This pulls in full-on PEMDAS now. These parentheses actually do mean something. So thank you, Rico. What I said earlier about dropping the parentheses, if there's a +1 in front, there is a +1 in front, but this parenthesis is now being multiplied by this parenthesis, and so it's different. Oscar? Foil? You foil. Now, who remembers what the word foil means? Yeah, a lot of you. Good. So first, outer, inner, last. Now, FOIL only refers to a binomial times a binomial. Is this a binomial times a binomial?
No.
No. So there is no FOIL. However, FOIL can instruct us here. What is the first two? FO. First outer, right? Here's what first outer looks like. First outer. What did I just distribute? All I did was distribute the x to the second parenthesis, right? What does ill look like? Inner, last. What did I just do? What did I just distribute?
5.
The 5. So FOIL is a shortcut representation of taking the first binomial and distributing the first term to every term in the second one, and then distributing the second term to every term in the second one. So everybody, if you have different colors, I really recommend it. But here's what we're going to do. Take the 10p and distribute it on top to all three terms in the second trinomial. So the 10p we're going to distribute on top. You have to draw those little rainbow lines. I call them rainbow lines. But we're going to distribute the 10p and multiply it by all three terms. And then what are we going to do with the -1?
The same thing.
Same thing, but on bottom, we're going to distribute the -1 to all three terms. How many multiplications are we doing?
6.
6. We're doing 6 multiplications. As a first guess, what type of polynomial are we going to end up with? Well, there will be 6 terms, so that could be a hexanomial. Nobody would say that. But some of them might combine, right? So at most, it could be a hexanomial. But it's probably terms are going to combine, and it'll be smaller than that. So let's go ahead and try it, folks. What's 10p times 100p squared? How many different parts of your brain do you need to use? 2. You have to do the 10 times 100, which is 1,000. And then you have to do the p times p squared. What's p times p squared? P cubed. Maybe you want to put the power of 1 on that p. So you know it's p to the 1 times p squared. 1 plus 2 is 3. So the first term is 1,000 p cubed. All right, we've done 1 term out of 6. So now continue multiplying. What's 10p times 10p?
100p squared.
100p squared. That's our next term, 100p squared. Continuing on, what's 10p times 1? 10p. That was nice and easy. Okay, we're done distributing the first term of the first binomial to all the terms of the second trinomial. Now we're going to distribute the second term of the first binomial to all the terms of the second trinomial. That was a mouthful, wasn't it? So now what's -1 times 100p squared?
-100p squared.
-100p squared. Should I write it all the way over here at the end? Or should I put it underneath the other p squared term I already have? I'm going to put it underneath the other p squared term that I already have, because that'll make it easy visually for me to combine those two like terms. Now, what's -1 times 10p? -10p. I'm going to put it below my other p term. And what's -1 times +1? Yeah, -1. Okay, so now we have how many terms? 1, 2, 3, 4, 5, 6, as predicted. How many of them combine? 2. Hi-ya! Hi-ya! Those cancel out. That was nice. And so our final answer is?
1,000p cubed -1.
Yeah, 1,000p cubed -1. The final answer was a binomial. That was a surprising result. All right. Folks, number 28 is yours. A very fun problem there. You're going to multiply a binomial times a trinomial. How many separate multiplications are you doing?
6.
6. I highly recommend you draw those rainbow lines. 3 distributions on top, and then 3 more distributions on bottom. Very carefully, using many different parts of your brain. Okay, so that's number 28 for you to do. Let me just check it. Oh my gosh, we finished. That's how far we wanted to go for the day. We're not finished for the semester, folks. We just finished for the day. Okay, now I said that I was going to look up my, in 1 second, I said I was going to look up my password, and then I never did. Jeez. Library friend. Let me pull it up real quick, and I'm going to show us all my math lab. We still have 4 minutes. I plan on using those 4 minutes to show you my math lab, so if you want to put your stuff away, that's fine, but nobody go anywhere. Oh, of course, I just remembered. Okay, so by the way, folks, in my opinion, really nicely done. I felt like this class went very well. I don't know if I called on everybody. I was really trying to call on a lot of people. I bet I missed a few of you, so I'll be sure to get you next time because I'd like everyone to participate. But yeah, we got through a good, solid chunk of material. By all means, if you have questions, please come see me right after class. Anybody who wants to come along, I'm going to my office. So we can all go together in a little train. You can fulfill your office hours requirements and ask me any questions you like. Okay, our class is Math 121. See you when you log in. You may have issues. Oh man, look at that message to me. You may have issues. That's not very nice of them. I mean, I probably do have issues, but geez. All right. Don't show me again. Don't show me again. All right, folks, this is what the homepage looks like. What you will only ever need to do is click on, well, I should really check before I tell you the wrong thing. Homework, that's it. You just click on homework over there on the left-hand side because that's all I've given you is homework. Now, taking a look here, you have chapter 5, 6, 7, 9, 10, 11. Those are the only chapters we're doing in the textbook. The first test, you will notice, is over chapter 5 and 11. I don't know why. I mean, I thought I put 11 right underneath 5. You can see the due dates are both February 1st. So February 1st, the due date for chapter 5 and chapter 11, that's your first homework assignment due on the day of the test. Right now, you are all well prepared to go home and click on chapter 5 and start doing problems. It says problems 1 through 56. You click on the first one. It pops up a second screen, and it's going to give you your problems to do. There we go. It takes a second to load. So there we go. There's your first problem. And you'll notice there's a little arrow button so you can click your way through the problems. The most important thing I want to show you is right over here on the right where it says question help. This is so important. Question help is awesome. Look at your examples or your options. It says help me solve this. It'll just literally walk you through it. It'll help you solve the problem, taking you all the way through the answer, and then it will give you a different problem to do, because it can't just tell you the answer. Or you can say view an example. It'll give you a different problem, show you how to do it so that you can still do the one that they gave you. It'll show you the section in the textbook relative to the question. You can click on Ask My Instructor, and it will send me an email with this question. And then you can just say, hey, Mr. G, I'm having trouble with this question. I tried this, but it didn't work. Make sure you say what you tried. Don't just email me and say, help. Right? Be specific. And then finally it says print if you wanted to print it out. You don't have to print it out if you don't want to. So anyway, that's your homework. That's the only thing you have to do. Last, I almost forgot to give you your midway quiz. Chapter 5 midway quiz. We are halfway through chapter 5. I have given you 8 questions. We've covered all except number 8. Oh, geez Louise. We're doing number 8 next class. So I might as well just, here, let me pass it out. And I'll just give you all a nice little tip. So everybody, here, will you please pass that down? This midway quiz is very short. You can use your notes. You can use your book. It's due next class, which is Tuesday. Oh, that's really good.
Yeah, and both of them are multiplied.
So we just vote. We just vote.
Yeah.
How much work should you show?
It's gonna be a, yeah.
Just put something in
Right,
the
because I can only give you partial credit if you show me work. And if you give me an answer without any work. Okay, everyone take a look at number 8.
Number 8, we did not technically do yet, but you're all capable of doing number 8. What would you do? I'm just giving you all the same hint, so it's fair. 10a minus 3 squared. What does squared mean?
Double the 10.
Multiply it times itself, right? Repeated multiplication, multiply times itself. So I'm going to write down what? And then, using the skill we just talked about, of course, you can just use FOIL. If you know FOIL, go ahead and use FOIL. But what we just did was talking about, you distribute the first number twice. So you're going to distribute the 10a to both of those. And then what would you do? Distribute the negative 3 to both of those. Okay? So I feel like it's only fair that I give you this little hint because we didn't technically get to this, even though we did, right? We did do this. So everybody, that's your hint. If you want to go and write that down on number 8 right now, that's fair game. Thank you very much, folks. I accidentally kept you 2 minutes early, but I'm not going to charge you for it. That was free. See you later. Here we go.
Wait a minute.
Oh, okay, great. Let me close up shop.
You got me.